Right now we'll also take some time to talk a little bit more about the angular momentum properties of these functions. And so we looked at this a little bit with the rigid rotator. And just as a reminder, if we operate the L squared operator on a spherical harmonic, on this eigenfunction of the L squared operator, we get that the angular momentum squared is equal to h bar squared times L plus 1 times the spherical harmonic, right? We get this is an eigenvalue equation. And same thing for the LZ operator. If we operate on the spherical harmonics, we get m h bar times y lm. So this tells us that the square of the angular momentum is equal to h bar squared times L plus 1. And the z component of the angular momentum is equal to h bar times m. So one question we might have is, why do I keep including z here, but what about x and y? Well, it turns out that these spherical harmonics are not eigenfunctions of these operators. And so we can't know the exact values of the x and y components of the angular momentum. So we know the magnitude of the angular momentum. We can say that the magnitude of L is the square root of the L squared operator, right? So we get L plus 1 times h bar. And we know the z component. We know LZ is m times h bar. But one thing that matters here is that Lx and Ly, they do not commute with Lz. So we can't know the exact values of Lx and Ly. So let's look at what this means. So if we consider a case where we have L equals 1, this is a p orbital, to jump ahead a little bit. We know what the absolute value of L is, so if we kind of plot the angular momentum on an axis here. All right, so this is our z component, and x and y are in the plane here. So this is kind of going like this. When m equals 0, we know that Lz is also equal to 0 because Lz is equal to m times h bar. All right, so that tells us that m equals 0. When m equals 1, we know that Lz is equal to h bar. And when m equals -1, we know that Lz is equal to negative h bar. So we're just using the eigenvalue equations that we have up above. So what that tells us is, if we kind of plot this, we know that when m equals 0, we know the length of our angular momentum vector is something like this. And we know roughly which way it points, but there is uncertainty as to the exact direction it points. So we know that how much total angular momentum it is, how fast it's spinning overall, but we don't know exactly which way it's pointing. So when m equals 0, all we know is that the angular momentum is pointed somewhere in the xy plane. And when m equals 1, it's pointed somewhere along this cone here. And in the next video, I'll get a slightly better image of this. So this is my drawing, but I'm going to put up an image of this so that you can see this. Right, so we know how fast it's spinning, and we don't know something about the direction, but we don't know it precisely. This is yet another instance of the uncertainty principle. But one thing we do know about all three of these possible states is that they are degenerate. The energy associated with all of them is exactly the same because the total angular momentum is exactly the same for all three.